What does the Dirichlet theorem says? That's the theorem we've been waiting for, the one that tells us under which conditions a function is going to have this trigonometric expansion that we have described just before. So Dirichlet was a German mathematician from the 19th century, so about the time Fourier described this kind of trigonometric series. Well, just a bit later, Dirichlet stated some necessary conditions. Right. So what did he find? He found that if f is periodic, well, you know that we can, even if your function is not periodic but is defined on a bounded interval, we can we can expand by periodicity this function so that it's going to be periodic. So we saw several ways of expanding by periodicity, just by simple periodicity, by odd periodization, or even periodization. Okay, and you remember, odd periodization gives you a trigonometric series only of sines, even periodizations only of cosines, and if ever you want to mix both, you can just do simple periodization. All right, what did he find? At the time we talked about class C1 functions, so they needed to be continuous with first derivative continuous. Then what he got was that the complex series associated to the function would converge uniformly on 0 to pi. Okay, uniformly just tells you that it does not depend on the point. It's not pointwise. It's more than just pointwise convergence. Okay, the functions converges pointwise, but it converges like on the whole interval at something like a similar speed. Well, whatever. We don't need that kind of subtleties this year. But then what's happening when you have defined the Lebesgue integral and you have defined functions from L2, if you remember, or functions from L1, okay, so square integrable functions, then you know that any function of L2 can be approximated by a sequence of C1 functions. This is something we stated briefly in the previous chapter. So we will have convergence for L2 functions. More precisely, this is something you have to remember. If x0 is a point of continuity for your function, then pointwise convergence of the trigonometric series to f of x0. And if ever it is a point of discontinuity, then you have pointwise convergence to the mean value. Okay, so that's very simple. Let's say your function is doing something like, well, goes to this value and then does something else, and you have found a way to, let's say this is going to be a periodic function, so maybe we can just erase a small part of this. Okay, so all right, so let's say we have this periodic function. You have periodized your function this way. What do we have? So what does it mean? It means that I will have periodized my function like this. Okay, so you can create the corresponding series and the corresponding Fourier series, whether you're using the complex expansion or just the trigonometric expansion, and you have convergence everywhere the function is continuous. So here, 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 and at points of discontinuity like this, the series pointwise converges to the mean value. Okay, so the series converges to the mean value of the function at the point of discontinuity. Okay, let's do the Hilbertian basis interpretation, because you know everything that we need for this, and that's really the beautiful part of that. Okay, so, well, one of the very beautiful part of this theoretical one. So, from previous chapter, you remember probably that a Hilbert space is the extension of the Euclidean space ID to function spaces of infinite dimensions. Right. So a Hilbert space, well, is that it's just a vector space where we have been able to define an inner product, and well, that is complete for the distance induced by this inner product. All right. So let's say what we have. The novelty is that we want to be able to consider complex functions. So what are we going to use as as an inner product in a complex space? Well, we have something a bit different than just symmetry. We have symmetry, but well, if you look at this, what we have in real functions, we have, if we have an inner product for real functions, we have that it's symmetric. That's something that's one of the important properties. Here, for complex ones, we need some kind of symmetry, but it's going to be equal to the conjugate of the symmetric expression. Okay, so don't forget. Well, if I'm not sure you are going to need that a lot, but if ever, don't forget that for complex inner products, this is what we are going to have. Then what else do we have? We have linearity as expected. And what does it give us? So particularity in complex spaces when you're looking at this kind of stuff. And you are going to get the complex conjugate of the coefficient of the scalar number that appears at the second input of your inner product. Okay, and then you also have positive definite, but that's the minimum requirement if we want to be able to define a norm. Okay, and so more precisely, when we talk about the L2 space of complex functions that are square integrable, what are we going to get? So we can define the inner product in that case as, so f inner product with g is going to be the integral of f times the conjugate of g. Okay, so that's very important when you are doing when you want to compute the norm that's that coming from this inner product. So you know it should be given by inner product of f with itself, and you want it to be equal to, well, some real value. And so you're going to have this definition. So what this definition gives you is that this is just the modulus of f. Okay, the modulus of f of any complex number that's given by well, the modulus square is given by f times its conjugate. Okay, so that's what we have, the modulus square of f, and we integrate that, and that's the norm, the L2 norm of a function. Okay, so that's in general when we define it on C, but now if we define it on well, if the input of your function is real, okay, and your function is going to be 2t periodic, all right, this is how we define the inner product. It's just going to be some slight normalization. So same definition, we've got f times the conjugate of g. Now we just integrate on one period, because obviously if your function is periodic, there are chances that if you integrate that on R, it's not going to converge at all. So you need to restrict yourself to just one period. So pay attention to the fact that we have expressed every time we have expressed our period as 2 times some value, okay? So that we do the integration from negative t to t, and so the size of the interval of integration is 2t, which is 1 period. Okay, and so we divide by the period size also. Okay, so that's a kind of normalization. That's the inner product we're going to use, and that has some importance for what's coming afterwards, because we're going to find some inequality some equality for that relates the coefficients of the series and the L2 norm of the function. Okay, now let's try to understand what this Dirichlet theorem means. It means actually that what does it say? It says that any function f in L2 can be described up to the discontinuity, so except for the discontinuity, can be described by a Fourier series. Okay, let's call Fourier series anything that is either a trigonometric series or the series with the complex exponential. Right. In other words, if you relate that to what we learned last year in general algebra, that means that the family of functions ei and x for n in Z is a spanning family for functions that are 2π periodic, okay, and in L2, right? So spanning just means that any element can be described as a linear combination of the basis, of items of the family, and it happens that we're going to need all of them. Okay, and that's an infinity of spanning elements, right, to create the infinite series, the infinite Fourier series, right? So that's why we have dimension. The dimension of those spaces is called infinite, because we need an infinite number of basis elements to describe them. Okay, I'm talking about bases because then we're going to see they are also linearly independent, and more than that, we have an orthogonal family, right? So that is something very interesting. We are going to check that the family E, I, and X for n in Z is, so we already said spanning, now we want to show that it's orthogonal. Okay, so what should I do? I should compute the inner product of EI and X with anything EI, K, X, for instance. Okay, so what is that? That's going to be 1 over 2 pi, integral between negative pi and pi. I'm just applying this inner product, right? So EI and X times EIKX, but conjugate of that, dx, right? So that's 1 over 2 pi, integral negative pi pi EINX. The conjugate of EIKX is minus IKX dx, and that, of course, is going to be equal to 1 over 2 pi times integral from negative pi to pi EIN minus KX dx. And, well, two things. Either if k is equal to n, what do we get? We get that EIN minus KX is equal to EI0x is equal to 1. Okay, so this EINX with itself, EINX, will be equal to 1 over 2 pi times negative pi pi integral of the 1 function, and so that's going to be equal to 1. All right, so that's normalized already. Now let's find the orthogonal sides. So if k is different from n, so I'm just doing the integration, and you know that's one of the functions we integrated not so long ago, like last week. So that's going to be 1 over n I n minus k, so which is supposed to be different from 0, EIN minus k x between negative pi and pi. And what do we get? So that's EIN minus k times pi, which is just going to be well, cosine of something times pi, all right? So minus 1 to the power n minus k, right? So cosine n minus k pi, sorry, that's going to be equal to negative 1 to the power n minus k. All right, plus this I times the sine of anything times pi is equal to 0, minus the cosine of minus n minus k, and you know that the cosine is an even function, so that's going to be equal to 0. Right? So in the end, what did we get? We obtained that EINK with EIK EINX with EIKX was equal to, let's use that Kronecker symbol, delta of NK, meaning equals to 1 if n is equal to k and 0 otherwise, right? So what do we get? This family, so for all n in Z, is spanning. That's the result of Dirichlet theorem. And orthogonal. And even orthonormal from what we have just given, right? And normalized. Excellent. So we've got an orthonormal basis of L2 EINX n. So the infinite sequence of those functions constitutes an orthonormal basis of L2, we said. L2 of periodic functions minus pi, that one way to say that, minus pi pair. So that's periodic functions that belong in L2 on negative pi.